this point, we've just been dealing with force vectors generally, okay? But there's another type of vector that we very commonly use in statics, and that's a position vector. And really, a position vector is just a vector that locates a point in space. So if I've got point P, as I do up here on the picture, okay, I can draw a straight line from some fixed origin up to that P. And the vector going from that origin up to P is my position vector. Okay? And I would write that just like I would write a force vector or any other vector in 3 dimensions, okay, with I, J, K components. Okay? So I would have an X distance, and this would just be like meters or feet, inches, millimeters, something like that. So I move some amount in the X direction, some amount in the Y direction, some amount in the Z direction to go from the origin to the point P. Okay, so that distance X, Y, and Z is written in Cartesian form, just like written right over here. Okay, so that's the absolute position, but a lot of times we want to know a relative position. That would be a position between 2 points, such as the position from A to B. And you'll see me typically write that as R sub AB. Okay, so in doing that, again, all I'm doing is I'm trying to figure out how much in the X, Y, and Z direction I move to go from A to B. Okay, well, I can write A and B in their vector form relative to the origin, just like we did up here. So I have the position vector A, the position vector B. Now, using vector addition, you can see that RA plus RAB, the vector between A and B, equals RB. And that's what I have written on this top equation right here. And that's just vector addition, right? This vector plus that vector equals this vector. So rearranging that and solving for the position vector between the 2 points, RAB, is just going to be the position of B minus the position A. It's always final minus initial, basically, where you're going minus where you started. Okay, so that can basically, I can do that for each component. Basically, final minus initial in the X direction, final minus initial in the Y, and final minus initial in the Z. Okay, and that's really how I can find a position vector between 2 points. Just take the final position minus the initial position. Okay. Now in class we'll do it a little bit differently when we solve problems. I think it's better just kind of think, okay, well, how much do I have to move in the X direction to go from A to B, in the Y direction from A to B, and so on. But mathematically it's just final minus initial. Okay. Now, why do we ultimately want to use this? Well, because oftentimes we write a force directed along a line. That would be like a cable or a rope, as I have here, right? I'm pulling on it with a force. I know that the force is directed through that cable. So if I can find the position of that cable, I should be able to write the force in Cartesian form. Basically, give the magnitude of that force a direction by knowing the position vector of this cable right here. So in order to do that, I need to talk about a unit vector. Okay, and a generalized unit vector, not the specific ones, the I, J, K, corresponding to the X, Y, Z. Okay, in general, a unit vector is nothing more than a dimensionless vector having a magnitude of 1 in some direction. So I have this U vector. I can give it a value of 1 and just say, hey, it's pointed in the direction of this cable, in the direction of this force, okay, in the direction of this position vector. Okay. So all I need to do is figure out how to get that to have a magnitude of 1 in that direction. And I do that simply by dividing any vector by that vector's magnitude. So any A vector divided by the A vector's magnitude will give me my unit vector. So similarly, I could take, if I know my force vector, I can take the force vector divided by the square root of the sum of the squares. That'll give me the unit vector. That would be a vector with magnitude 1 in the direction of my force vector. Likewise, and what we typically do is we use the position vector. So if I know the position from A to B, if I can find that R vector going from A to B, okay, I can find the magnitude of it by taking the square root of the sum of the squares and just divide that R vector by its magnitude and get that unit vector. Okay? Then from that, I can actually write my force in Cartesian form. So if I know, say, I've got 10 pounds, I've got some magnitude of force up here, I can take that magnitude of the force times the unit vector. That will give me my force vector. And it's essentially just rearranging this equation, just bringing F over to this side. Okay? Now, I substitute in what I know about my unit vector was just the position vector divided by its magnitude, which is generally easier to find, right? I can measure the length of this cable, its position. Okay, I can find its position vector. I take its position vector divided by its length or its magnitude. Okay, that will give me the unit vector. And I can write that force along that line as the magnitude of the force times the position vector from A to B divided by the magnitude or the length of that cable from A to B, which gives me the unit vector, gives me the direction, which again I'm multiplying by my magnitude of my force. Alright, so here's an example using position vectors to find the resultant force. So again, I've got two forces here. I've got a force B going from A to B along some cable, 600 newtons, and force C, which is 450 newtons, going from A to C. Okay, and I want to know the magnitude of those two forces added together, the resultant force that's acting at A. Okay, so I start with vector B, and again, what I'm going to do is I'm going to take that force vector, the 600 newtons, and I'm going to multiply it by the unit vector going from A to B. A unit vector, again, is magnitude of 1, basically just gives me the direction without changing the magnitude. So to find that unit vector, I just find the position vector from A to B, okay, and divide it by its magnitude. Now, moving from A to B, okay, again, it's just final minus initial in all of the x, y, and z components. So B is at -5 in the x direction, okay, minus +5 in the x direction for point A. Okay, so B is at -2.5 in the y direction, okay, minus a -1.5 in the x direction. Okay, and K in the z direction, B is at 2, A is at 0, so 2 minus 0. So the way I actually generally do this is say, okay, how much do I go from A to B? And I see I go 0.5 plus 1.5, so I go 2 in the x direction. Okay, in the y direction I go -1, because I go from -1.5 to -2.5, and in the z direction I go up 2. So I would just call that what would I call that? I would call that -2, -1, 2. Okay. So square root of that is just going to be the square root of the sum of the squares. That gives me the magnitude of the position vector. And I'm left with my unit vector, which is just -2/3, -1/3, and +2/3. And again, if I took the square root of the sum of the squares of this, I'd find that the magnitude of this is 1, which is what a unit vector is. So that's the unit vector from A to B. Now I simply multiply that times the 600 to get this force vector. So I'm writing the force vector B in Cartesian form just by taking the 600 newtons times the unit vector from A to B, given right here. So I take the 600 times -2/3, 600 times -1/3, 600 times 2/3, and I get -400, -200, plus 400. So that's the vector form of FB. And again, I'm doing the same approach that I do with any vector addition, right? Each force in Cartesian form, sum up the x, sum up the y, sum up the z. So I'm starting by writing the forces in Cartesian form. So now I have to do the same thing for C. So I start with the unit vector. So in the x direction, I move, let's see here, I move 0.5, so I move -2 in the x direction. In the y direction, I move 1.5, so I move 2 in the y direction. And in the z direction, I go from 0 up to 3.5, So I get 3.5 K. So basically I get negative 2, positive 2, 3.5. So taking the square root of the sum of the squares to get the magnitude, I get a unit vector of negative 4 ninths plus 4 ninths plus 7 ninths. Taking that unit vector times the 450 gives me my force vector for C. So I take 450 times negative 4 ninths, get negative 200. 450 times 4 ninths, positive 200. 450 times 7 ninths, positive 350. Okay, so at this point now it's very simple. I've got my force vectors written in Cartesian form. To find the resultant, I just sum up the i's, sum up the j's, sum up the k's, and I get a resultant vector of negative 600i, which is negative 400 minus 200. My j's cancel, and I get 750k. So finding the resultant of that, I just take the square root of the sum of the squares, and I get 960.47 newtons. So again, write the forces in Cartesian form, sum up the x's, sum up the y's, sum up the z's, take the square root of the sum of the squares to find the magnitude. To write those forces again, it's just the magnitude of the force times the unit vector, which is the position vector divided by its magnitude.
In this problem, we want to determine the magnitude of the resultant force, knowing that FB, the force from A to B, is 700 newtons, and FC has a magnitude of 560 newtons. So to start this, I'm going to write FB and FC in the Cartesian form. And in order to do that, I need to take those magnitudes, 700 and 560, times the unit vector in the direction from A to B and A to C. And that unit vector is found by taking the position vector going from A to B divided by the magnitude of that position vector, which is essentially the length from A to B. Okay, so moving from A to B, okay, I end at 2, start at 0, so I move 2 in the x direction, I move minus 3 in the y direction, and I move negative 6 in the z direction to go from A to B. Okay, so again, 2 minus 3 minus 6. Okay. The magnitude of that is basically 2 squared plus 3 squared plus 6 squared, which actually gives me 7. So my unit vector to go from A to B is 2/7 I minus 3/7 j minus 6/7 k. So 2 over 7, 3 over 7, 6 over 7. Okay, so the force vector, FB, I just take that unit vector, which just gives me my direction, and I multiply it by 700 newtons. So 700 times that unit vector I found above gives me this force equation right here for B. So I'll do the same thing for C there. Okay, so moving in the x direction, I move 3, going from 0 to 3. In the y direction, I move 2. In the positive direction from 0 to 2. And then in the k direction, I again move negative 6. So I get 3 plus 2 minus 6 for my x, y, z components. The magnitude of this one is again square root of the sum of the squares. So it's going to be 3 squared plus 2 squared plus 6 squared, which again is 7. So I get 3/7 plus 2/7 j minus 6/7 k. That's the unit vector going from A to C. That gives me the direction of that force. Again, I get that from the position vector divided by the magnitude of that position vector, or the length of that cable. So FC is then 560 times that unit vector, and those numbers are given right here. So this is FB written in Cartesian form. That's that 700 newtons put into its x, y, and z components. And this is the 560 newtons put in its x, y, and z components. Okay, so now that I've got those forces, I do just like I've done before in finding resultants. Add up my x's, add up my y's, and add up my z's. Okay, so here's FB. I add it to FC, so I plus I is 440. J plus J gives me negative 140. And then K plus K gives me a negative 1080. Then to find my Magnitude, I just take the square root of the sum of the squares. Okay, so 440 squared plus 140 squared plus 1080 squared, and I get 1175 newtons, or 1.17 kilonewtons. So again, you just write each force in Cartesian form, sum up your x's, y's, and z's to get your resultant force. Okay, in order to write those in Cartesian form, you just take the magnitude of the force times the unit vector, which is the position vector of the cable going in the direction of the force. That position vector divided by its magnitude, which is the length of the cable. That gives you your unit vector. Multiply that times the magnitude of the force to give you the force vector written in Cartesian form.